Hi once again. Today it's our concluding session with a workshop named ZKP Under the Hood, which will be delivered by Marija Mikić. I'd like to invite our today's guest to the stage. Hi Maria, how are you?
Hi, I'm great. How are you?
Yeah, me too. Thank you so much. I'd like to ask you to say a couple of introductory words about yourself, about your background, and we'll be starting to share your screen.
Okay, thank you. My name is Marija Mikić. I work as senior researcher in team 33207, which is R&D department in the company Alik 42, but also I am professor at Faculty of Mathematics in Belgrade, Serbia, and head of department for differential equations. So my background is theoretical mathematics. And one more thing, I'm also co-founder of Mathematical Academy. Mathematical Academy is some kind of private school where we are working with talents in the field of mathematics, physics, and cryptography. And for example, this year, our students, the best of them, obtained 41 medals on the state competition. So we are very proud of that. So today's topic is zero knowledge proofs. I think that you already knows a lot about zero knowledge proofs. And first I want just to mention that when we are thinking about zero knowledge proof, what we mean by zero knowledge proof, we mean that zero knowledge proofs are cryptographic methods that we use in order to prove that we have some secret, but we don't want to reveal anything about our secret. So what we want to prove that we just have that secret. And this topic today will be about zero knowledge proof, but under the hood. So we want to explain how we can create this proving system. So there are two main components to obtain this. The first of them is arithmetization, and the second one are polynomial commitments. So when we combine different arithmetics and polynomial commitments, we will obtain different zero knowledge proofs. We will obtain Starks or Snarks. So the first topic here today will be about arithmetization. What is arithmetization? Well, there are different types of arithmetization. For example, we can use rank 1 constraint system as GROD 16. Using this, we can use algebraic intermediate representation, Starks using this representation, or we can use Plonk or something else. But this arithmetization that we mentioned a moment ago, this is maybe most known arithmetization. So what we mean by arithmetization? What we want to have? Then first we want some statement, some program to transform into arithmetical circuit. So we will have gates and wires, and after that we want to obtain a system of constraints, mathematical equations, and after that we want to represent this with polynomial constraints. So we want to represent all these things using just one polynomial, and we want to see how we can do it. So first we want to talk a little bit about arithmetical circuits. What are arithmetical circuits? I think that the best way to explain this is using the example. So, for example, I want to prove to someone that I know a number a, such that when I multiply a by a and add number 1, I will obtain number b, and this number b is a public number. So, in order to create a arithmetical circuit that will represent my claim, I will create this circuit. So I will have left wire and right wire, and I want in this gate to have multiplication. So I want to multiply left wire and right wire. I want that my left wire be number A and right, of course, number A, and the result will be output wire, and this output wire will be, of course, A squared. And after this, I want to add number 1 in order to prove my claim. And if the result, the output wire of this arithmetical circuit is number b, that is public, then I create an arithmetical circuit that represents my claim. So this is idea behind. I want to create a arithmetical circuit that contains wires and gates, and we use two operation, multiplication and addition, in order to prove our claim. And for example, if I want to prove to someone that I know some preimage of hash function SHA-256, then I will get an arithmetical circuit that contain about 20,000 gates. So our arithmetical circuit from this example was really short, but here we have 20,000 gates. So um, in order to create arithmetical circuit that represent here, that is represent here in the example 2, we need to use 20,000 gates, so a lot of gates. And now we want to explain how we can transform this arithmetical circuit into a system of constraints. So we will explain, because we can use different types of arithmetization, we will explain this on one example. This is Plonk. Plonk is proving system that we are using when we are using zero knowledge proofs, but of course we can use different proving systems. But for understanding here, we will explain on this example. So we will continue with our example that we already had. Our claim is that we know this small a such that a multiplied by a, and when we add number 1, we obtain b, and b is public. Now what I want to represent this arithmetical circuit using mathematical equations. So I can use two types of constraints. The first type of constraints are gate constraints, and these constraints will be related to these gates. So if we consider this first gate, we can conclude that the output wire is a result of multiplying the left wire and the right wire. So we can transform this into equation. We will multiply left wire from the first gate. This index represents the first gate, with right wire from the first gate, and minus output wire of the first gate, and we will obtain 0. So this equation here will represent this first gate. In order to represent the second gate, because in our example we have just two gates, what we need to do, we need to add to this left wire constant. This constant is number 1, and we will obtain that L2 plus number 1 minus output wire from the second gate is 0. So with this equation we represent the second gate. And here just to note that constants we will not use as wires. So we will have that here we have a number, and this number will not be right wire. And we can see from this that with these two equations we represent our gates. But here we have some copy constraints. And why this is important? Because here, for example, if the public number is 17, and for example I have number a that is 4, if I put as my inputs my secret numbers here, that L1 and R1 is 4, then I will obtain as a result number 17. But of course, if I add here that number 2 and here in right wire number 8 as output wire of the first gate, I will obtain 16. And after adding number 1, I will obtain the same result. And why this can happen? Because here with gate constraints, we did not write that we cannot have different values from these our inputs. So in order that our mathematical equation represents really the our claim and our arithmetical circuit, we need to be carefully. So we need to add that left wire the first input, and the right wire, the second input, secret input, of course, are equals. And of course, we need to create a connection between output wire of the first gate and the a left wire of the second gate. And we can see that this is the same wire, so we need to add that output of the first gate is equal to left wire on the second gate. And we can see here that with this 4 equation, we totally represented our arithmetical circuit. So what we done so far, we started with our claim, then we represent claim as arithmetical circuit, and then we represent arithmetical circuit as system of mathematical equations. And now what we want to generalize this. We want to create a general equation that can represent any gate. Today, I will not talk about these copy constraints, and if anyone is interested, we can use some permutation, and you can read it in the original paper Planck that was written by Ariel and others. But I think that we don't have a lot of time today, and we would not explain this in detail. So I will just explain how we can obtain gate constraints, and here in the presentation you have a link to original paper Planck, and here this will be general equation that we can use in order to represent any gate constraints. And why? What is here? Here, this is left wire. This is index of the gate. So for example, if we have this first equation, I want to put appropriate coefficients here, corresponding coefficients here, in order to create to obtain this first equation. So left wire here is not alone. Here in our equation 1, there is left wire but multiplied by right wire, and we have here multiplication of left and right wire. So in order to obtain this equation 1, I will use that corresponding coefficient to multiplication of our gates are 1. So this coefficient will be number 1. And here I will obtain, when I fix index that is 1, I will obtain this. And of course, I need to obtain this. In order to obtain this, I will use that coefficient that represent output wire is -1. And other coefficients, this coefficient represent constant in our equation. Here we don't have constants, so this coefficient will be 0. If we have a lone right wire, not multiplied with left wire, we will obtain here number 1, but because we don't have a lone right wire, this coefficient for the first equation will be 0, and here we will also obtain 0. So when we use that this coefficient is 0, 0, -1, 0, and 1, we will obtain the first equation. But we want that every equation to be represented by this general equation. In order to obtain this, what we will do for second equation, we will in the second equation we don't have multiplication of left and right wires, so this coefficient will be 0. We have alone left wire, so this coefficient with left wire will be 1. We don't have right wire, so this coefficient with right wire will be 0. We have output wire, so we will have here -1. We have constant. This constant here is 1, so this constant will be 1, and we will obtain the second equation. So what we can conclude, that we can obtain these two equations that are connected with our arithmetical circuit from this general equation. And we can obtain any gate from this general equation. So this is important. So we have one equation that can represent every gate. So if we go back and we think about our example, this one, where we had hash function SHA-256, we have there about 20,000 gates. So when we go back, we will have 20,000 of equations that represent gates from this arithmetical circuit. A lot of equation and a lot of constants that we will have in this equation. And we will have, we need to have memory to store all those coefficients if we want to store this and to represent our arithmetical circuit. So instead of doing this, what we can do, we want that this system of equation be represented only by one polynomial. So we can transform this system of equation, and just to note, this system of equation does not need to be a linear, because we can have multiplication of left and right wires. So we want to have just one polynomial. In order to obtain this, what we can do? Well, I want to create polynomial which represents left wire. So we can think about this. Let's create polynomial such that the value of polynomial in number one, this number one represents number of the gate in our arithmetical circuit, to be L1, this value of our inputs. And because we have just two gates, the value of left wire in a second gate to be L2. So there are so many polynomials. For many polynomials, these conditions will hold. But we want to have just one polynomial that represents these conditions. So what we want to achieve, we want to find the polynomial with the smallest degree that fully fill these conditions. In order to do this, what we need to do? So what is this if we think from the geometrical perspective? So we have 2 points. The first point will be the point with coordinates 1 and L1, and the second one with coordinate 2 and L2. We want to find polynomial of the smallest degree. This will be the polynomial of degree 1. So this will be the linear function. From geometrical perspective, this will be line. So I want to find the line that crossing to these 2 points, and I can find in Euclidean space, I can find just one line that are connecting these 2 points. So there is a unique polynomial that will represent these conditions. And because I know this condition, I of course can calculate this polynomial. For example, you can use also Lagrange method of interpolation if you want to calculate this polynomial. And in the same way, we can think in order to create polynomial that will represent right wires and of course output wires. So we will obtain polynomial that represents left wires, right wires, output wires. But of course, we will have polynomials that represents these corresponding coefficients. So we will have a lot of polynomials that we need to create. And this polynomial are connecting in this way, because our secret polynomial, this polynomial f, will be result of a generalized equation. So this polynomial f will be result of multiplication of polynomial that represents left wire and correspond polynomial and polynomial that represents polynomial of corresponding coefficients to the left wires, plus a polynomial that represents right wires, multiplied by polynomial that represents corresponding coefficients to the right wires, plus polynomial that represents output wires, plus polynomial that represents constants, and plus product of polynomials that represents left wires. We can see the connection here, right wires, and this polynomial that represents corresponding coefficients with this multiplication. So here, what is important to note here, because we can see here our left wire and right wire will be secret inputs. These inputs are private inputs, and we want to prove that we know these inputs. So we don't want to reveal these secret inputs. So what we can make public is the way how we create this arithmetical circuit. So we can say that this corresponding coefficient will be public, because we want to prove that we play by rules and we create arithmetical circuit that represent our claim. But we do not want to reveal our secret information. In order to do this, with output wire of the first gate, we don't want to reveal this information too, because with this information we obtain some information about our secret inputs. So left, right output wires will be our secrets here, and these corresponding coefficients and polynomial, of course, here that represents our corresponding coefficients, are public. So we create a arithmetical circuit that is such that some of coefficients are public and some of them are private, in order to do not reveal our secret. So from this, what we done so far, we start with arithmetical circuit. We represent this arithmetical circuit as a system of equations, mathematical equations, then generalize these gate constraints, and after that I create just one polynomial, this polynomial f, that will represent and how will represent these gate constraints. When I fix this small x here to be 1, I will obtain this equation. We can see it if we change that x is number 1. So when I fix that x is 1, I will obtain this left hand side of the first equation. When I fix that f is 2, I will obtain the second. At the left hand side of second equation. So with fixing the values of this little x, I will obtain an equation that represents appropriate gate. So this is the general idea. And just one thing to note, here we are using natural numbers, but in the original paper they are using roots of unity, but they are using it just for optimization. And I think that the best way to explain this, you can think that we are using just natural numbers, so because root of unity is just for optimization reason. So the first thing was arithmetization, and we explained how arithmetization how we can obtain arithmetization in Plonk. And now we want to explain polynomial commitments, but um, one part of polynomial commitments are trusted setup. So let's start with trusted setup. What is trusted setup and why we need it? There are different types of trusted setup. There are transparent setup. Starks are using transparent setups, but there are also trusted setup. There are difference because in transparent setups there are no such kind of secret that we need to believe that this secret was used and after using destroyed. But here we need to believe that this secret that was using was destroyed, because if this secret is not destroyed, maybe someone can cheat and create proofs that are not true, but they will accept it as true proofs. So there are two types of trusted setup. Trusted setup per circuit, for example, ROD 16 are using this trusted setup, and for example, trusted universal setup, which is independent from the circuit, and this trusted setup are using Blanc. So how we can create trusted setup? Maybe the most known creation of trusted setup was when Zcash created trusted setup. It was 8 years ago, I think, and there was 6 people in generation of this trusted setup, and every person that was in this generation of trusted setup create one part of this secret. So if we have, for example, 4 people, all 4 people will add a part of this secret, and from these parts they obtain one number, and this number is that secret number that are needed in trusted setup. And in this ceremony of trusted setup that we mentioned a moment ago, that Zcash are created, after this creation, then they destroyed their computers, and they were live stream this ceremony. So what is trusted setup, and why we are using this setup when we are using snarks? The first thing that we will use elliptic curve. Elliptic curve, I think that I don't have here in presentation. This is just a curve that have some shape that are similar to some fish. You can think about this in this way. So this is just a curve, and we need to have some cyclic group on this curve. When we are talking about cyclic group, what is cyclic group? Cyclic group is just a group of some elements when we can use one element and one operation in order to obtain all elements in this set. For example, we have a cyclic group when we watch our clock. For example, we go from number 1 to 12, and after that we go again 1 to 12, and so we have a circle. And when we add number 1 to number 1, we obtain number 2, and so on. So we use modular arithmetics in order to obtain this. But we can think here that we have some elliptic curve, and we have some point on elliptic curve that is generator point. So this point will be used as a point that is very, very important for us, and using this point, adding this point to itself, we will obtain every element in this cyclic group on elliptic curve. So the cyclic group will have order p, and p will be prime number. So we will obtain p elements of this set, and this number here is infinity point on elliptic curve. So what is here important? First, we will have the ceremony of generation of trusted setup. So a lot of people today, when this ceremony when we want to have ceremony now, we will have about 100 and thousands of people that will be included from different countries in the world, and all of these people will give their secrets in order to create this just one secret that we here note with a small s. And this secret will be number from the finite field. So this will be the number. And after that, we will obtain public parameters, and these public parameters will be used by prover and verifier. So when we have zero knowledge proofs, we have two parts. We have prover, person who want to prove the claim, and verifier. We can think about people, but verifier can be smart contract or some program. We have one part that want to prove something, and we have the second part that we verify this claim, accept or reject the claim. So both of these sides will using these public parameters. And what are these public parameters? Well, this will generator point, the important point that we mentioned a moment ago from the elliptic curve, and we will multiply this generator point from the elliptic curve with this secret number from ceremony of trusted setup, and the secret number squared multiplied by this generator point, and so on. So if someone knows this point, because S is just a number and this is the point, this point has two coordinates, so this will be point on elliptic curve. When someone knows this point, he cannot calculate this little s if we choose that number p is very big prime number. Why? Because he needs to solve discrete logarithm problem on elliptic curve, and in real times our computer cannot solve this problem, but quantum computers can. But for now we are safe. So these will be public parameters that will be used by prover and verifier, and after generation of these public parameters, this secret from trusted setup needs to be destroyed. If this secret is not destroyed, that some people can falsify the proof. So because of that, because we have some secret and we need to believe that this secret is permanently destroyed, we call this setup trusted setup. And why we need this trusted setup? Because we want to have the proof that is short, and the verification time for verification we want to be short too. In order to obtain this, we need to have some pre-processing setup to obtain that proof is short and proving time is also short. So argument system. What we want to have with zero knowledge proofs? Well, we have prover, as we mentioned a moment ago, we have verifier. And prover wants to convince the verifier that he knows some secret, some witness, so that when he puts this witness as private inputs in his arithmetical circuit, he will obtain the results of this arithmetical circuit with B0. If 0 is the result, then the verifier will accept this proof. So what we have here, we have public arithmetical circuit. When we say public arithmetical circuit, what we mean by this, we mean that all these coefficients that represent our arithmetical circuit in the gate constraints are public. So we have public statement. I want to prove that I know, for example, some number 8 such that a multiplied by a plus 1 is public number b. This is public statement. So, yeah, I want to prove this, but my secret number a is my witness. So only prover knows this witness, but prover and verifier, both of them, knows this public statement. So verifier needs to know this public statement in order to check the validity of this statement. So this is argument system, and with argument system we will have some interaction between prover and verifier, as we can see here. And after this interaction, verifier will choose to accept or reject the proof. So this is argument system. And now we want to add some things. What we want to add, the first thing that we want to add is to have non-interactive pre-processing argument system. So here, for example, if we have prover and verifier and we have interaction between prover and verifier, this is exhausted, because for example, we can think about if prover wants to prove to someone that he really knows some secret information, and after that he wants to prove to someone else, he needs to repeat all the process. And when we do not have interaction, prover can just create proof and everybody can verify the proof. And because of that, it's very important to not have interaction, to have non-interactive zero knowledge proof. So here we will not have interaction, just prover will send the proof to the verifier, and after sending this, verifier will choose rather to accept or reject the proof. And we will have pre-processing setup. What is that? We will use this, for example, for snarks. We will use these public parameters from the trusted setup. So we mentioned a moment ago here that we will have these public parameters that we obtain using this secret from the trusted setup. So now we want to use these public parameters, and this will be public parameters for the prover, and this will be public parameters for verifier. So prover will know public statement, secret witness, secret of prover, and public parameters from the prover, and verifier will know public statement and public parameters. Prover will send the proof to the verifier, and verifier choose to accept or reject the proof. So we want to have this, and we want to have three things more. We want to have completeness, soundness, and zero knowledge. So what is completeness? So zero knowledge proofs are not mathematical proofs. They are probabilistic proofs. So there is always small probability that someone can cheat, but this probability can be negligible, and this probability can be small, that small that we can choose how small to be. So first, completeness. If prover knows public statement and has a secret witness, and create arithmetical circuit and put this public statements and secret witness into arithmetical circuit, and obtain that output of this circuit is number 0, that then verifier with probability 1 needs to accept this proof. So if prover really has the secret input, then verifier needs to accept the proof as valid. So this is completeness. The soundness, a verifier will accept the proof. If a verifier accepts the proof, then the prover probably knows witness such that output from the arithmetical circuit is 0. So if we use contraposition of this statement, we will obtain that if prover does not know secret witness in order to result of arithmetical circuit is 0, then probability that verifier will accept this proof is negligible. So this is soundness, and from these two properties we can be sure that if prover knows the proof, verifier will accept the proof with probability 1. But if prover does not know the secret witness, then verifier with high probability will reject this proof. And of course, zero knowledge. Zero knowledge with all these public and private parameters, verifier will not learn anything about this secret information, secret inputs from the prover. And I just want to note that when we are using snarks are using trusted setup. They are important here because without zero knowledge property, we can have snarks and we can have zero knowledge snarks. Zero knowledge snark has this property, but snarks do not have this property, but they also have all these properties that we are talking about. So you can think about this. If I want to prove someone that I know preimage of SHA-256 hash function, and my preimage is 1 GB in size. If I want to prove someone that I know this preimage, I can send this preimage to verifier, and he will check hashing this preimage that I really have this preimage. But my proof will be very long proof because I need to send 1 GB of data, and verifier needs to have a lot of time in order to check validity of my proof. But with this, with snarks, without zero knowledge property, we can obtain short proofs and fast verification. So I can prove that I know preimage of SHA-256 hash function, and my proof can be very short, not 1 GB of data, and verifier can verify very, very fast that I really have preimage. So I don't need to reveal my secret information, and of course I don't need to send 1 GB of data in order to prove this. But if I want to have also zero knowledge and I don't want to reveal my preimage, I will use these ZK snarks. So let's continue now. Commitments. We said that we have two components that are important for building snarks. One of them was arithmetization, and we explained it. The second one was polynomial commitments. Polynomial commitments are using setup. Because of that, we talk about setup. And of course, they are commitments. So we will talk what commitments are. Commitment scheme is, as we can see here from the slide, it's cryptographic primitive that allows one to commit to chosen value or statement while keeping it hidden from the others, with ability to reveal the commitment value later. This example here is interesting for me because I'm professor, so I can for example, if I want to commit that I will give the same task for the exam for my student, I can hash the text of the exam and publish it to my website. And every student, when come to exam, can hash the tasks and see that they obtain the task that I was committed to give them, and they can be sure that they obtain the results that I wanted to give them. And of course, everything is clear that I was not malicious, and I not give for someone the exam with some other tasks. So this is important commitments. And here we have functional commitments. One case of functional commitments are polynomial commitments that we will use. So what we want to have with commitments? So with polynomial commitments, this f will be polynomial, and first prover will commit that he will use this polynomial. And why polynomial? Because we was talking about with arithmetization, from arithmetical circuit we will obtain constraints, and after that we will obtain one polynomial. And because of that, this polynomial have in himself some secret values. We don't want to reveal anything about our polynomial, and we want to commit to this polynomial, but not revealing anything about this secret polynomial. And after that, verifier will send the challenge to the prover. If we have an interaction. If we don't have interaction, we can obtain non-interactive zero knowledge proof when we use Fiat-Shamir transformation. So we can obtain easily, but is more simple to explain with interaction. And because of that, we have interaction in this slide. And after that, prover will send the value of polynomial in this x, and this will be y. But for example, if we want to have zero knowledge proof, he will not send this y, he will mask it, and he will send some kind of commitments to this value, and of course zero knowledge proof. After that, verifier will accept or reject the proof. So what we have with functional commitments, you can think about polynomial commitments. We have setup phase. We talk about setup phase. So we have generation of secret. We have multiply people that are here in order to give some values to this secret, to obtain this general secret. And from this, we will obtain some public parameters that will be used by prover and verifier. Then we will have commit phase. We want that a prover commit that he will use the polynomial that we obtain from arithmetical circuit. And after that, we have evaluation phase. Evaluation phase is here. Verifier will send a challenge to the prover, and prover will answer to this challenge by calculating the value of his polynomial in this challenge and mask it in some way. And after that, verifier will accept or reject the proof. So polynomial commitments, there are so many polynomial commitment scheme. Here we can see some of them, but probably the most known commitment scheme is KZG commitment scheme that are using trusted setups and elliptic curve pairings. And here Fry that using hash functions is also very famous, and we are using in Starks. So this is the maybe the most difficult part of the presentation. We want to explain how KZG works. So what we want to have with KZG polynomial commitment scheme. First, we have three phases: the trusted setup phase, commitment phase, and after that, we will have evaluation phase. With setup phase, we choose elliptic curve. We choose cyclic group on elliptic curve. So we use trusted setup. This is S from ceremony of generation of trusted setup. We use this secret in order to obtain our public parameters. Our public parameters for prover and verifiers are generator point on elliptic curve, generator point multiply by this secret, and the powers of this secret multiply by generator point. After that, we destroy this secret. This is setup phase. The commitment phase, prover will commit that he will use this polynomial. And what is commitment? Commitment is a result of multiplying this value of secret in polynomial f multiplied by generator point on elliptic curve. But this secret S was destroyed. We can see here. And how someone can calculate this? Because prover will use these public parameters. And how we can achieve this? Well, prover knows his polynomial, so he knows coefficients of this polynomial. And when we change that value, we fix the value of x by this s and multiply f of s, in point s with generator point on elliptic curve, we will obtain this result. But this result, when we change that this is, for example, h2, this is, for example, h1, and so on, these commitments can be calculated using public parameters. So prover can calculate the commitment to this polynomial without knowing this secret, of course. So this is magic behind this. And this is a very important theorem, Schwarz-Zipper lemma. What the Schwarz-Zipper lemma tells us, when we have a polynomial with degree that is less or equal to d, and we pick some random point from the final field, the probability that we will choose that this point will be zero of our polynomial is less or equal than d divided by p, where p is a prime number that represents our finite field, and the d is degree of our polynomial. So when we are using zero knowledge proofs, this number, prime number p, will be about 2 to the power of 256, and the degree will be less or equal than 2 to the power of 40. So the probability will be very, very small that someone can cheat. And the consequence of this Schwarz-Zippel lemma is that if we have two different polynomials that had degree less or equal to d, and we pick some random number from the finite field, the probability that we will choose the number such that polynomials in this number are equals is negligible. So we will use that if we pick a number and obtain that we have that two polynomials are equal in this point, that these polynomials are probably identical. And this is crucial when we are using zero knowledge proofs. So here we have some statements that we are using from high school math. So if we have that value of polynomial in x0 is y, then x0 is root of f minus y. So this is equal that polynomial x minus x0 divides polynomial f minus y. So there exists quotient polynomial such that q multiplied by x minus x0 is equal to f minus y. And we want that verifier somehow checks this equality. So in order to check this equality, verifier cannot check in every x from the finite field, but we can use Schwarz-Zippel lemma. Maybe if we choose some x randomly, then send, for example, to prover, maybe if this holds in one point, with high probability using Schwarz-Zippel lemma, we can conclude that this is these two polynomials are equal. So here we in evaluation phase we can see that proof that will send prover to the verifier will have in self commitment to this quotient polynomial. So prover will calculate this quotient polynomial and send commitment to this quotient polynomial. This will be the part of the proof, and of course the x will be challenge that will send verifier to prover, and the prover will answer to this challenge calculating the value of his polynomial in this x and multiply by g, generator point on elliptic curve, because when he multiply with this, verifier cannot know this y, but maybe he can check the validity of his statement. So just I think that we maybe have just 5 minutes, so I will go to the point. If a verifier could check this statement, then what this statement means? This statement means that we fixed that x is equal to s. So when we fix this and multiply by g, we will have almost equality because we fixed the value, but we will obtain commitment of a polynomial q. And this is just when we fix x, here we will be s. And of course, here we have f in a number s and multiply by g, and this is commitment of our function, minus y multiplied by g. And if this equality holds, using Schwarzschild lemma, verifier can be sure with very, very high probability that prover really have this secret witness. But can verifier can check the validity of this statement? Well, the answer is no, because verifier does not know little s. And how we can achieve this? Well, we need to use elliptic curve pairings. We cannot say we cannot solve this problem so easy. So we need to use advanced math in order to obtain this. And I don't have time enough to explain how we will use it using elliptic curve pairings, but I just want to explain three things that are very, very important. So here, the main idea was that we have prover Maria and verifier Andrea. In order to Maria prove that Maria really have a secret witness that is hidden here in this polynomial f, then Maria needs to calculate value of this polynomial in the challenge that Andrea will send to Maria. But first, Maria needs to go to arithmetical circuit, and we need to be sure that this polynomial is obtained as a result of creation arithmetical circuit. And of course, we want that Maria be able to falsify the proof. In order to do this, we need to go to the wires, and Maria needs to send these polynomials that represent left, right, output wires, and so on. And we need to add more things. We need to add commitments to these polynomials in order to obtain that Maria cannot falsify the proof. And then Andrea will send a challenge, and Maria will answer to this challenge with these commitments, and she will send the proof. This is commitment of quotient polynomial. And what will be the statement that verifier will check? Well, this will be the statement, and this statement are using elliptic curve pairings, and we don't have time for this, but I just want to note this. This is bilinear map, and this bilinear map is here here have some properties that obtain to commute scalars that are in some from some field, and we have two subgroups on elliptic curve and so on, but we cannot explain here in 2 minutes, and because of that I just want to finish with this. If we want really to have verification and to be sure with high probability that someone have secret input, then in order to use KZG commitment polynomial scheme, we need to use also elliptic curve pairings. And I think that this is on time. Thank you. If you have questions, I'm here.
Okay, yes, thank you so much, Maria, for delivering this workshop. I need to quickly check if we have questions in the live chats. Give me a second, please.
Of
Just
course.
a moment. Yeah. It seems like there are no questions for now. And I think you made the topic pretty clear and easy to understand if there are no questions in the live chat. But still, if we get some questions after we publish this recording on our YouTube channel on other platforms that we have, and if we will be receiving some questions, I will let you know. But that was really useful and detailed. So sadly that we couldn't go through the pages, but still we are always open to receive your questions. Thank you once again, Maria, for coming and for doing these topics so easy to understand. And thanks to everyone who've been watching this in a live session. I think it's now the right time to move on to our conclusion of the conference. I hope to see everyone in 15 seconds.